Okay, so
Okay,
this
sir.
is okay. So we have this repair. So why we are concerned about this area? Because this area where all the load has been transferred from this to this, because now we have removed these sections. So how it happened is, so the load will go here. There's a force come to this plate, and then it will go, and then we meet these rivets, and then transfer up, and the balance will go to the next rivet, go up. So they will go up both, and then will come down, and then another remaining will go and come down to the next rivet. So that is how the load transfer. It's just like water flow. So that is how the load transfer across this angle. And this has become complicated because the angle has damaged. We have removed the section and we have changed the load path. That's why in design repair we should not we should be trying not to change the load path as much as possible, because the change the load path can cause another problem, which is mostly a fatigue problem, because the change of load path will cause stresses, and the higher stress will cause the fatigue life to be reduced. Okay, so this is how the load transfer carried across. That's why area A2 by 3 fastener, that's why they make very distinguished area here. So every time you see this example repair, you can see the gray shaded area, and they will say this is the rivets area. Because we are talking about the forces that we talk about is always talk about this area. Question? Are you following? Not following?
Yes, sir.
Okay, now let's look at the material. Every time we do repair, we have to first specify the material. Just like you do the drawing, you will work out first the bill of material. Okay, here is all the explanation of material. So you can see the label it. Number one is, where is one? One here is joining section. So always say doubler, and sometimes people call it joining section. In this case, the Airbus has said that this is joining section. Why joining section? Like I have shown you here. Okay, is joining the area here. Okay, is joining the section where portion of the section has been removed. Joining section. So the join. If we don't put this doubler or joining section, we are not able to transfer the load across these two areas. Two is section insert. Section insert, we always say is a section insert. So here is number two. So this is filler. Like again, I say again, why we have to have this is filler to prevent water to be collected, because water is a source of corrosion. And the aircraft design requirement also has stated that no water or moisture trapped in the aircraft structure. So that's why we don't want anything trapped. That's why we have to put a filler. And you can see the repair which I have shown you previously earlier. If you damage your vertical flange and they are not, we don't bother to put any filler because it's nothing will trap there. It's open area. Okay. Then we have rivets countersunk. So rivet here underneath here all countersunk because here is a aircraft internal outer skin. So air will flow through here, and you don't have a countersunk, those reverse head will cause a lot of drags. And for some aircraft which is certified to RVSM, reduce vertical minimum, reduce vertical minimum, reduce RVSM separated minima, where the aircraft can fly within only 1,000 feet across among each other, I mean on top of each other. Then those only to be certified for this kind of flight operation, you have to have RVSM certified. In one of those major, I mean primary requirement for the airline to be certified, the aircraft must meet all these aerodynamic smoothness requirement. So if you have a round head, you don't install countersunk, and then you have round head which cause drag, so you are already not compliant to the aerodynamic smoothness requirement. And then we have this here rivets. This is universal head. Here we're not concerned about the aerodynamic. We do not concern about aerodynamic smoothness. That's why we can just install universal rivets. Any questions? That's why most importantly, when you do the exercise, when you do the final, when you do the exam, you have to specify, you have to label this component. So if not, then you get a very poor mark. So you have to label what are these components, what material or this component made of. Okay, next one is we're talking about those are material, and here we have the material that we use, for example, pre-treatment for painting, sealant, cleaning agent, structure paint. So those are consumable material. Those are material we use to complete the repair. So it also been certified what kind of sealant we use, what kind of paint to be used. Next, let's look at a few notes. And I hope when you do assignment, when you come to the point where you need to write the detailed installation procedure for the aircraft, we have to include all this painting, cabin plating if required as part of the instruction to do the repair, especially on the making or fabricating the parts. Okay, look at the note here. We have to see first note say all part fastener have to be installed with PR1436. So these are sealant. So fasteners or wet install. Wet install is you dip the fastener into the sealant and then you push through the hole. We don't just dry, just put into the hole without any sealant. So the installation requirement of fastener, we have to have sealant. Break all the sharp edges, and we do not want all the sharp edges because sharp edges contributing to fatigue. All dimension is in millimeter if you are working on the European aircraft, but if you are working on US aircraft, all the unit will be in imperial, so it will be in inches. All parts to be adjusted on the aircraft. All dimensions are in millimeters, all parts to be adjusted in the aircraft. One thing that you see, if you go through all the example that I've shown you, there's no dimension there because you have to determine the dimension by yourself based on the information given. For example, if you are asked to make a plate and the plate is So if you ask them to fabricate a plate, what is the dimension? You won't get the dimension because you have to calculate the dimension itself. Yes, sir. That's why I said to be adjusted during installation. So I said this plate, they have two rivets on the plate. So how to calculate the dimension? So here is a mystery. How? So what we have here is we have ED, we have H distance here, we have H distance on this side, and between the rivet we call it either rivet spacing or sometimes people call it pitch. So that is what we define in between the rivets. However, what is the ED? What is the spacing? By default, the manual has said that H distance is 2 times diameter. And then spacing for pitch is 4 diameter. So these are the rule of thumb being used in designing the aircraft structure repair. H distance is 2, spacing pitch 4. Usually H distance for most structure you still can go up to 1.5, but the structure is still good. However, to be conservative, we put 2. So by having that, if you say, let's say, the fastener is 4 millimeter. Okay, 4 millimeter. And what is the dimension? Okay, what is the dimension? So how to calculate the dimension? Any idea? Oops. How to calculate the dimension X? This dimension here. So it will be H distance is 2D. So 2 times 4 millimeter times the 2, because you have another one. Outside we have 2 sides. 2D, ED, 2ED, so times 2 for this plate. Okay, times 2. Or 2, 2D, 2 places plus 5 millimeter. 5 So that will be the length. So you don't have to tell them the length, they will calculate the length themselves. And if you tell them the length, you may be in error because we do not know exactly what are the factor of the area. So you have to rely on the mechanics to calculate the length required for the plate and also uh, how to install them. That's why I'm explaining you about the notes given by Airbus, as I mentioned to be adjusted. So that is one of example. Any questions? Okay, go to the
No,
next
sir.
note. Okay, go to the next note. The next note talking about bend radii. Okay, bend radii. So the bend radii of the repair must be made so that the outside radius of the inner meeting part is greater than the radius inside. Okay, let's say we have this angle and we repair. It says that bend radii of repair part must be made so that the outer side, this radii, okay, must be made so that the radius or outer radius of the inner nesting part. Okay. So we have this. So here it must fit in or else is a problem. Okay. Now what is the next note? Okay, next note is very important because most of you miss this one. Very simple and very easy to understand the analogy of this. So original part 20242 thickness 1.6. Double part, as much as possible, as best as possible, use the old material type. So 204042 we use 20, we use T2, we use 20 alloy 20 24 dash 42 as well, similar. Okay, the only thing is the thickness is different because the thickness, the rule of the thickness is the repair doubler is 1 gauge higher. So that's true here. So 1.6 on the original, the doubler is 1.8. So that is they are following this guideline. Okay, now we go to the next analysis. It's where we need to determine the load. Okay. Okay, here we have to copy back. You have to determine the material allowables from the table, which I have shown you earlier, which is table 517011, table 2, which give you all this FTU, FTY, FCY, FSU, FBRU, and EC. So the value is there in the table. And we use A or B, L or LT. Remember, we have some discussion on that. So we have A, V, L, LT, LT. Okay, here we have to say A value are used in LT, used here. So LTA. To be conservative, we use LTA. So they did copy here in the table and determine FTU, FTY, and you have to calculate between to be used in the ultimate, either ultimate or FTY time 1.5. So why we are concerned about this? Because we are, remember, we are talking about failure point. So it can fail a lot later. However, there's already permanent information. This is not acceptable by the, it's not acceptable for the failure. Okay. So that's why we have to multiply one, there is 1.5 to the FTY. So 345 is the FTY is 230. Okay. 230 times 1.5, you got 345. So now either you use 345 or 390. Remember of what we have discussed earlier. We have the stress strain curve. There's a line here. As we apply the stress, it will be deformed. At one point, it come down and it come down and fail. So anything beyond this point, it will come, if you release, you come back to a point which is no longer back to the original. So this we consider as permanent deformation. So we have to make sure when you do the analysis, we are on the right track. So here is FTU. And somewhere here is yield. FT yield. When you pass a FT yield, you already have the permanent information. So you must make sure whether you're on the right track. So you multiply 1.5 to the FTY. So you have to select which is the highest, the minimum, sorry. The minimum of FTY, FTU, which is 390. Okay, this is cannot run away from that because this is what they have done the test, 390 FTU. And you multiply 1.5 to the FTY, which you get 23345. So 345 is lower than 390. So we have to be, we are conservative. We say if fail at 345, so we use analysis. The value is at 345. Any questions?
No, sir. Everything clear.
Okay. Everything clear. Okay, next. So now we have to look at the fastener, calculate the fastener, determine the fastener, select the fastener, determine the load, and also calculate the number of fastener required to install the doubler. Okay. So here, so fastener and rivets. Fastener is general term used. Rivet is one of the type. You may have bolt, you may have nut, and rivet also there are many rivets, the high lock, jaw bolt, lock bolt. So for this, what they decided, what we can determine is we use countersunk. Remember, we need to have one row of rivets underneath the skin to use countersunk. It's countersunk 100 degrees. This is 4 diameter in diameter, 4 mm in diameter, and the rivets MS 20426 AD rivets. And then the data that we use is you need to find what is the strength, joint strength. So how much this rivet can take. It's not mean that the rivet can fail, but for skin, for thin skin, you need to use the failure point when the material fails, because the material is very thin. So in this case, we use a 20426 AD, and we also looking at 1 each per row. So we have 2 rows, 3 rivets. That is what we have sketched. And then we go to the table 517013 from table 7, appropriate for the MS 20426 AD, and we determine the fastener strength is 2330 Newton. Okay, so all the calculation we've done based on this 2330 as far as rivet is concerned. So all the calculation will be done on the original, because original is thinner. So the thinner section will fail first compared to the thicker sections. No questions? Okay, allowable fastener. Okay. Next is determine the allowable fastener. So we have 2330, which is the fastener strength. How to calculate the number of fastener? We have to calculate the load loss. What are the load loss at the area and how much we want to put the load back, and the number of fastener will be the one required to transfer the load across. Remember, we are just explaining to you about transfer the load and area of fastener and where the load are transferred. So as far as we also need to look at the crippling and buckling of the repair section. So it has a note here based on assessment. It does not calculate for this case because it's obvious. The upper flange fastener ensures stability between the original part and the doubler. So that's why we also install doubler on upper flange, even though it's not to transfer the load across, but it to provide the structure stability. Now let's calculate the load loss. So what we're doing here, we are trying to calculate the load. The load we use to calculate the stress, and the stress we compare to the material stress. In order for you to calculate the load, you need to have load or force equal to stress times area, cross-sectional areas. So for this situation, you need to calculate the cross-sectional area. So the cross-sectional area or loss So this is cross-sectional area of the loss. So how to calculate? We have to calculate the area equal. So we cut at 15 inch, sorry, 15 mm. Meanwhile, minus 4, there's already a hole, and then that is effective length, and then we multiply with the thickness. Okay, time thickness. Time thickness. Area loss. For area of the doubler, we have we make a cut. We make a section here. So 18.4 minus 4, where there are fasteners, then time the thickness as well. And you can see here by looking at the thickness, also we know the cross-section area will be higher. So the load carrying capability of the doubler obviously will be higher. Okay. And then we calculate. We show here the calculations. So we show the calculation of the area. And this is a cross-section area. This is vertical. This is horizontal flange. This is thickness. This is cross-section area. And then you multiply, remember, we decided to use 345 megapascal. And this is not the force that we have lost, or the load that we lost, mean that we have lost this capability because of the area we removed. Stress times the area, we got this force. This force is something that we have lost. We need to recover the force, and that's why we install the doubler, and we calculate the doubler area. We multiply with the doubler area to the tensile stress that we establish, either by 1.5 times FTY or the FTU itself. And by doing that, we have 9,000 over Newton force that we get from installing the doubler. And then you can see here the doubler is having a higher capability than the original part. So obviously the repair is good. But how much good? In order to know how much good, that's why we calculate the reserve factor or reserve factor, sorry. We calculate reserve factor by just dividing the load established for doubler over the load loss, and you get 1.5. So it's higher than the minimum certification requirement is 1.5. I mean, it's a par, sorry, not higher, it's a par, similar. Okay, now we calculate the number of rivets. Remember the gray shaded area that we've been discussing earlier. So we cover the area. We calculate the rivets required to carry the load. So we have this fastener. We have decided earlier 2,330 Newton, and a single shear. And we have the load loss 6,072 divided by the fastener strength 2330, we got 2.61 fastener required to transport the load. So we round up to 3. So that's why you can see 2 rows, 3 fasteners. 3 fasteners in a row. That is enough to cover the load loss due to the cut. Any questions so far? Can you follow? Or you
Yes, sir.
guys tired? Ready for holiday?